Really glad to be here today. So I'm Gombert. I'm a software engineer at Kitware, and I work full-time on ParaView for the last few years. Okay, so the goal today is to present you the current state of post-processing in FEniCS, what's possible, and also the tools that we currently provide and the innovations we have that could be of use for this solver. So yeah, let's get started. Just before that, I've had quite the question quite a few times. ParaView is open source, a permissive license, it's free. Is there a company behind it? So yeah, the response is yes. We are actually quite a big company. We have 200 over the world. We have an office in Lyon, in France, where we are about 30 people, among which 10 of us are working on ParaView full-time. Yeah, we do mostly open source software. It's a permissive license, mostly BSD, so you can do whatever you want with it. It's been working for the last 25 years. And second question I had a lot, so how do you make money with open source? I also have an answer to that. We do training on ParaView. If you want your team to be trained and operational on ParaView, we can train you. We also provide support if you have any questions. We also do custom developments if you want a custom plugin, custom reader, or anything. And if you're a researcher, we can also collaborate on the grants, if they're European grants, French grants, or anything like that. Okay. So ParaView, I assume most of you are familiar with the software. So it's a software that was made in 2002 and has kept evolving since then. It's open source, multi-platform, and it's made for data analysis, especially for 3D data analysis. It's suited for HPC workflows, which means that it can be deployed at scale on a HPC, and then using a client, you can visualize your meshes at scale. All right. Yeah. ParaView can be applied to many application domains. Most of you do finite elements, and some of you CFD. It can also be applied to medical stuff. We have a lot of utilities to read medical data, do volume rendering and that kind of stuff. We also do a lot of particles rendering if you do particle simulation, as well as many other things like geoscience, astrophysics. Like people do a lot of things with ParaView. So ParaView is a full ecosystem, so you're mostly familiar with the Qt client, but as I mentioned, it can also be controlled from a HPC server, so you can deploy it at scale and it reads in parallel very fast. It can also be deployed in the web using a framework called Tram. I don't know if you've noticed on the FEniCS docs, you have a tab where it's an interactive view, so that's made with Tram and PyVista. So you can share your work online very easily using that. We also integrate with Jupyter notebooks. I noticed that the FEniCS community loves Jupyter notebooks, and I do too. It can also do OpenXR, so virtual reality interaction. That's really a fun one too. And also Catalyst. Catalyst is a framework for in situ visualization. I'll talk more about that later because it's really interesting. Okay, so let's review the tools currently available for FEniCS post-processing. The one I've seen today, this morning especially, is PyVista. It's really easy to plug in. It's a simple library. Actually, it's based on the same library as ParaView, which is called VTK. I'm also a core developer of VTK. So it has all the power of VTK, so everything you can do in VTK, you can also do it in PyVista. The greatest limitation of PyVista is that it does not scale. It cannot be deployed in a HPC server. When you do it with MPI, yeah, you have to bring in all the data in the same node, so it's not very efficient. So that's the main limitation of PyVista. And also you have to script it, so you cannot explore the data freely as you can do in ParaView. So that's a different framework. And then ParaView, so I replicated the same visualization of the basic FEniCS example in ParaView. So it's basically the same thing because the rendering API is mostly the same. What's great about FEniCS is that it's mostly implemented by Jorgen and Chris Richardson. It has a lot of output formats so that you can use. I've bolded the last one because I think it's the most relevant one currently. But you can also export your meshes as XDMF. It's not recommended anymore, as a classic VTK file. So it's the VTU and PVD files. And the VTX, which is also not maintained anymore. So my recommendation for that is really to use the VTK HDF file format. It's the most efficient we have. It's actively developed, and we plan to maintain it long term. So more on the VTK HDF format. So it's something we launched a few years ago. I'm the main developer of it currently. It's based on a technology called HDF5, which is made for HPC and large data. What's great about it is that you don't depend on VTK for writing files. You can just use the HDF library, and from any language, just write your files. It supports natively MPI partitioning for writing and reading, so you can read and write from the same file. It's very, very, very efficient. My favorite feature maybe would be static mesh. If your mesh does not change between time steps, you can just keep writing it, and it will consume less memory and less disk space. And yeah, it supports natively the quadratic and biquadratic cells as well as the Lagrange cells. So that's a plus for that. Okay, I wanted to have some prospective subjects, things that we have implemented in ParaView and VTK and that I would love to see in FEniCS. I was discussing that earlier. We've got a new data model which is called VTK cell grid. So it's basically a generalization of high order cells. So classically, you need to define scalar values at the edges, at the vertices of the cells. And with using quadratic cells, you can define also at the edges and at the center. But this time, we have made a data model on which you can define values anywhere you want on faces themselves or on edges. This way, you can use the same grid for discontinuous cells, which was not possible before. So this is very experimental. It's been here for a couple of years. It's not implemented yet in the file format I presented before. But yeah, I think it's a great opportunity to support the cell that Johnny described just a few minutes ago. The second thing I wanted to discuss with you and present is in situ support. So we have a framework called ParaView Catalyst, where you can do your post-processing without writing your file to disk. So the idea is you take the points and the scalar values that you have in memory, you send them to another process running ParaView, and post-process them directly in memory. So you skip writing them to disk, and it's very fast and efficient. So yeah, I don't have the video because it's a PDF. Should have thought about that. So it's much quicker to get results on your data, and you skip the writing step that can be very costly. So yeah, this is something I would love to see implemented in the future for FEniCS. It's been implemented in many solvers very successfully in the past. So yeah, especially for high performance and HPC runs and big simulations, it could be very valuable. Okay, that's not FEniCS, but it looked cool. So yeah, this is a CFD simulation. We do have time for a few questions.
Thank you very much. Any questions for Louis? Yes, go ahead, Chris.
I was just wondering what kind of time frame you're thinking of for landing the VTK cell grid into the VTK HDF.
Yeah, it's a big effort. I would love to do it, but first I would like the VTK cell grid to be stable, more stable than it is currently, because it's a research project. It's highly experimental. So yeah, I think in the next years it should be here. But yeah, no guarantee. I'm very hopeful that we can manage to fit that in here. Not that there is already a format for VTK cell grid that handles especially discontinuous Galerkin cells. But yeah, it's implemented not in HDF, but in the old VTK legacy file.
Thank you. Other questions? Please go ahead.
Yeah, there's a bit of a whine. In Debian, or well, I use Kali Linux, the hacker Debian, but the opt version of ParaView doesn't load properly, at least to open window and maybe.
I have no idea. Download the version from ParaView.org. That's the version we support. Usually the ParaView versions that the package manager ship are incomplete. They lack a few dependencies. So just go to paraview.org/download and take the latest version, and you're all set.
Much bigger,
Yeah.
things to download.
Yeah.
Okay, thank you.
So you said about the on-the-fly visualization with Catalyst, right? So what about the memory requirements? So like when we are solving really large problems which are already taking up a lot of memory, and how it balances down. So is there anything?
Most of the time, it should be zero copy, which means all the data that you send to the visualization process are pointers to your data. And then just using the pointers, you can reconstitute the mesh and then process it from here. So it should be lighter in memory, in theory, if you do the thing properly.
Okay, but how does this work? I need to start the ParaView, or will work, and then I can run my simulation in FEniCS and visualize results in the ParaView, or how is that?
Yeah, it's true. I didn't explain how it works. What you do is that you set an environment variable pointing to the ParaView Python implementation. And then there is a common API, which is Catalyst. It's a Python package, basically, that you just do Catalyst execute. And if FEniCS has the binding, so the binding of the mesh to the format required by Catalyst, it loads in runtime the ParaView implementation and runs the Python pipeline that you planned before. I can do a demo if you want.
I have a question.
Yes.
Thank you for coming to us. Is it possible, so you said that you support Jupyter notebooks and Python. Is it possible to create pictures, making screenshots, as you demonstrated at the beginning, without opening ParaView GUI and directly from the Python script?
Yeah, absolutely. If you're in the interface of ParaView, you just click File, Save State. You save your state to Python, and then it will save a Python file, which is basically your pipeline. And then from here, if you run the Python file and just save the screenshot at the end using the command, it should work.
Okay, so I cannot like just abandon ParaView GUI. At some point, I need to at least open it once.
I mean, you can script everything manually, but it will take more time. The usual workflow is you do your thing in the GUI, then save to Python, and then run the script, the Python script on its own.
I think the question is more specifically on the PNGX flow.
Yeah. It's like the PyVista workflow. I try to reproduce with the ParaView.
I can show you how it's done. It's really easy, but you can totally do it using PyPython. Yeah.
Right. Other questions for Louis? I have one actually. You said that we should move away from VTX because it's no longer the future. I feel like my group literally just transitioned from XEMF to VTX, and now you're telling me that I need to move to VTK-HDF. So
I'm sorry.
it's a bit of a tough question, but
yeah.
How long until we need to transition away from VTK-HDF into the future?
That's a tough question. That's only me, but I think that VTK-HDF will be maintained long time. I've been working on it.
Thank you.
And on the scale from 1 to 10, how sure you are?
I mean, the VTU files have been working for the past 10, 15 years, so I think we're safe. VTX was an experiment, mostly.
You know, we all had memes in our pronunciation. We should have had the meme of the 15 standards, and now there's 15 standards. Anyway.
But this one is great. I show you that VTK-HDF is the great one.
They all were great. Any last question? Go ahead, Jürgen.
Maybe a comment. I also think VTK-HDF is a good idea.
I know you do.
Yes.
All right, we still have a bit of time for questions, but otherwise, I'm happy to remain ahead of schedule. And yeah, let's thank Louis again.